In today's video, we're going to take a look at the rules for simplifying radical expressions. And these are rules that you're probably familiar with already. Maybe you just haven't written them down formally before, but you've used them when you've simplified some basic radicals. We're just going to kick it up a few notches by looking at some more sophisticated problems involving these rules. So the first rule we're going to look at is the product rule. And before we start looking at the rules, we have to pay attention to the types of numbers we're going to use in the rules. Keep in mind that we want our radicals to simplify as real numbers. And the numbers we use for our indices have to be natural numbers. And again, the first rule we're going to look at is the product rule. And the product rule simply states that if we have two expressions with the same indices, the nth root of A and the nth root of B, and we're trying to multiply those, we're allowed to put those together under the same umbrella as one big radical. And we have to have the same indices in order to be able to do this. So one example we want to look at here is, let's say we had the fourth root of 8y times the fourth root of 3r squared. Well, the rule simply states that we can just now make one big radical and call this the fourth root of 24yr squared. And we just put it into one big radical rather than having two separate radicals. This isn't a new rule. You've actually used this rule before. When we talk about things like root 50, we know that root 50 is the same as root 25 times root 2. And we want to break it up that way because we know that root 25, that's a perfect square, and we get 5 root 2. So usually we are going in this direction where we have a radical we want to simplify and we break it up and go here. So if you think about the product rule, usually we start with this part and end up breaking it up. But we can go in the opposite direction as well. The next rule we're going to look at is the quotient rule. And the quotient rule says that if we have a division, the nth root of A over B, that can be split up as two separate radicals, the nth root of A over the nth root of B. And an example of this is, let's say we had to do the fifth root of x over 32. That means that we can do the fifth root of x over the fifth root of 32. And that's convenient. The fifth root of x, there's not much I can do with there. But I certainly know what the fifth root of 32 is, or at least if I think long enough, I might be able to get it, and that is 2. And that would simplify that way. Okay, so these are rules, not new rules, but we're just refining it a little bit and bringing in the variables as well. So in this section, we're going to be simplifying a lot of radicals, and we have to think about what does it really mean to simplify a radical. And there's actually 4 rules that we need to satisfy in order to simplify a radical. And in this slide, I've simply taken the page from your textbook and done a scan of it to show you the simplified radical rules. But here in the middle, you can see the conditions for simplified radical, and there's 4 of them, and they're there in your notes. So at this point, you might want to think about pausing the video to copy them down in your notes. So I'll do a little space here to let you pause. Okay, so either you're written them down or you're just waiting on me here. So as we go through the rules, let's talk about them just a little bit. Rule 1 says the radicand, so the stuff inside the radical, has no factor raised to a power greater or equal than to the index. Well, that would mean something like this. Let's say if we had the fourth root of 2 to the 5th power. Well, we would know that we could simplify that. So the radicand has a power higher than that of the index. That would indicate that this could be simplified further. And it would mean that somehow I would be able to pull a 2 out of this radical. And we know that this is the same as 2 times the fourth root of 2. So that's rule 1. Rule 2 is that the radicand has no fractions. What I can't have lying around, and I'll move down here because there's some space, is I cannot have something like root x over 2. We'd want to split that up as root x over root 2 and then use our rules to deal with that. That brings us to root 3. No denominator contains a radical. So if I continue this simplification, having a radical in the denominator is illegal. The math police will come after you. And in the next section, we're going to talk about rationalizing a little bit more. So for right now, I'm just going to kind of leave it be. Just respect that we can't have a radical in the denominator. And we'll be dealing with that down the road. And the last rule is exponents in the radicand and the index of the radical have no common factor except for 1. That's a little convoluted, but it's simply by example. If we had the cube root of x to the 6th power, 3 and 6 here, they have the same factor, which is 3, and that would indicate that this could be simplified further, and this one can be. It's simply x squared. So those are the 4 rules for knowing when a radical is simplified. So we're going to finish off by looking at 3 examples here, and here's our first example. So if we have root 200, x to the 7th, q to the 8th. I'm going to show you kind of a long way to do this one. By our rules, this means that we're allowed to take this and split it up. Root 200 can become root 100 times root 2. K to the 7th can be k to the 6th times k. And q to the 8th can just come along for the ride. So I use the product rule to kind of deconstruct what I have here and turn it into smaller factors. And I didn't just choose these things randomly. I chose all these factors randomly because I knew that they could simplify. I know that root 100 is 10. I know that root k to the 6 is k cubed. And I know that q to the 8th, the square root of that, is q to the 4th power. Okay, and then I have the 2 and the k hanging out for the ride. So this one would come out as 10 k cubed, q to the 4th, and I did not leave enough room here, root 2k. And one small little thing here I have to deal with, because this is a square root problem. I do have to deal with k cubed, the eventuality that could be something that's negative, so I do have to put the absolute value bars around k cubed. So I'm going to clean this up a little bit. I have 10 q to the 4th, absolute value k cubed, root 2k. It's kind of messy, but that is now simplified. All right, here's our second example. The opposite of the 4th root of 32 y to the 9th. Oh, and actually, I want to go back to that original problem. You notice in this problem, I did use the product rule to kind of write this all out. To be totally honest, that's just for example here. That's really not a necessary step. It's quite okay if you start with this problem and said to yourself, hey, root 200, I know that that is 10 root 2. K to the 7th, if you understood that k cubed would come out and the k would stay inside, and q to the 8th, you understood that q to the 4th would come out. And I think through practice you start to realize that. And you do, again, have to be careful about these absolute value bars that you'd have to have around the k cubed. So I don't want to imply that you have to do this deconstruction every single time. Okay, back to our second example. The opposite of the 4th root of 32y to the 9th. Again, I will deconstruct this one just so that we're clear on what's happening. I have to think about 4th roots. There's not many 4th roots I know, but I do know the 4th root of 16. And I would have the 4th root of 2 because they would multiply to make my 32. Y to the 9th, I would need the 4th root of y to the 8th and the 4th root of y. Now I can break this down. I have the opposite of 2y to the 8th, and then the 4th power, the 4th root of 2y. And again, this is y to the 4th. I think I said y to the 8th there. That's going to be 2y. Oh, excuse me. That's a little mistake there. All right, that's a little low shell mistake. Let's get my eraser. That's this piece here. Oops. All right. Now I'm making all kinds of mistakes. The 4th root of y to the 8th, that's y squared. That should be y squared there. So sometimes we make mistakes late in the video. And there we are. Last problem. Wow, root 7 times the cube root of 2. Doesn't look obvious that I can do much with these guys right now because they don't have the same index, and the product rule and the quotient rule both say that they have the same index. So what can I do? So we're going to do a little novel approach here. I'm going to rewrite these guys. Root 7 is 7 to the 1/2 power. And the cube root of 2 is 2 to the 1/3 power. Still doesn't look real promising. But here's what I'm going to try with it now. I'm going to make these exponents here have the same denominator. So this would be 7 to the 3/6 power times 2 to the 2/6 power. And now I'm going to go ahead and I'm going to rewrite them now as 2/6, excuse me. I'm going to rewrite them now as radicals. 7 to the 3/6 means 7 cubed, but the 6th root of that. And 2 to the 2/6 power means 2 squared and the 6th root of that. And now look what just happened. I now have two radicals that have the same index. That means I can invoke the product rule here. I can make this one radical. This is now the 6th root of 7 cubed times 2 squared. And if I get my calculator out, I see that that is the 6th root of 1,372. How sweet is that? Isn't that kind of nice? 6th root of 1,372. And that is simplified because there's nothing in here. There's no 6th power of anything inside of there that I can do anything with, and I've made it as one radical. That's a little bit of extreme example, but notice how we went from something that looked pretty messy to something that's at least one radical, even though it's a 6th root. So product rule, quotient rule, things we've seen before, we're just amping up the sophistication a little bit.